First of all, a very good morning to all of you, and all those who are teachers, happy Teachers Day. Yeah. Thanks to Dr. Anjali and IIT Kanpur for inviting me to deliver a talk during this training program. I am sure that you are hearing robotics, and you have been into robotics for I mean, at least many of you would be doing some kind of robotics work, and some of you may be new to robotics. But in any case, my talk is not going to be too technical. I will be talking more on the development work that I have been doing, the research work going on, and I will touch upon one or two topics, so that you will get a flavor of what kind of research work I am doing at present. So, before going to the research the topic, let me give you a brief introduction about the research work or the type of work what I do or what we do in our lab. To give you a brief idea of what are the things happening there in my lab. So, I started my research in the area of underwater robotics. That actually I started when I was doing my postdoctoral fellowship at Nanyang Technological University in Singapore. That was my first exposure to underwater robotics. And then after coming back to IIT Madras, I continued this work, and then was part of a work where we developed an autonomous underwater robot for Indian Navy. You can see actually this is the the actual robot which was deployed, and it is undergoing sea trials, which is actually 300 kilogram weight and around 5 meters of length, 1 meter, 1.5 meter width, which can go up to a depth of around 200 meters at present. So, the main job what we did in this was not in the hardware part. Hardware was done by DRDO with their private participation. So, our job was basically to look at the dynamics and control of these robots. And even before we really make the robot, we would like to understand what will be the dynamic behavior of the robot when the robot is deployed into the water. And since there is no communication, you need to program everything, and you need to have a good control algorithm, control strategy. So, our job was basically to look into the brain of the robot rather than the body of the robot. So, we did a complete 6 degree of freedom dynamic simulation, and modeling, and then simulation, then controller design, and then verification of the controller algorithm, etc., etc. And we were part of the trial process also. So, with that this robot was deployed in water and in the sea near in the Bay of Bengal near Visakhapatnam, and it is still the trials are going on. So, in that area in underwater robotics, we have been looking at a few other aspects also. One is the dynamic station keeping control of a remotely operated vehicle. So, the first one was an autonomous underwater vehicle. A remotely operated vehicle is one which is teleoperated. That means you can sit somewhere, and then through a cable you can send the control signals and control the robot. And this kind of robot, one major issue is that when there is a current, underwater current is there, the robot will be actually carried away by the current. And if you want the robot to stand at stay at one position and then do some inspection or some kind of data collection, it will not be able to do that, because the current will take it away from that position. So, this problem is known as the station keeping. That means you want the robot to keep the position and then do the task. And so, we were working on this, and then we came up with a new control strategy, a dynamic station keeping control strategy, where the robot even before the current really take the robot forward away from it, it can actually predict the position changes using some kind of force sensors. We try to measure the current velocity, and using the velocity and the robot model, we try to predict what could be the way in which the robot will move. And even before the robot starts moving, the thrusters will start the control action and then try to maintain the position. That is the dynamic station keeping of control strategy. We have filed a patent for this on this strategy, as well as the measurement of forces. We use simple strain gauge sensors to measure the current and then predict the position changes. And another one was on multi-point potential field method for obstacle avoidance. So, most of these things are available on in the literature. So, in case you are interested, you can just search for some of these keywords, and you will see the papers already there in the literature. A multi-point potential field method is again a new method for avoiding obstacles, or actually identifying the obstacle and then trying to find out the size of the obstacle, and then see a method to have a better or safe avoidance of these obstacles. And another one was an AUV manipulator system, that is, if you have a manipulator attached to the AUV, to this robot you attach a manipulator, and this manipulator, when it is doing some task, there will be some kind of dynamic interaction between this robot and the manipulator. And so, what kind of effect will be there, and how do you control the position or trajectory of the manipulator when even if there is a change in the position of this robot? That was the AUV manipulator system. And one of the current work we are, these are actually slightly old work, we have already completed all these works and then it is available in the literature. So, this is one of the recent work we have been doing at present. We have developed a very small variable buoyancy module, which actually works on the principle of metallic bellows. So, as you know, underwater the buoyancy is one of the forces freely available. That means, whenever you put something in the water, there will be a force acting on it, and this force can actually be used for many it can be effectively used for getting underwater manipulation. And we actually came up with one of my students is still working on it, variable buoyancy module. So, he has developed a simple module which can actually change its size depending on a control signal. It can change the size of it, and therefore, it can go up and down without having any additional external force. And by cascading this kind of multiple modules, we can get large actuation forces, and these forces can be used for multiple applications in underwater. And one of the application is like you want especially again in a defense application, you want something to be lying on the floor of the sea for a long period, like 12 months or 24 months. You want this to be in the water, and it won't come up unless there is a need. So, it will be having multiple sensors, it will be searching for, or it will be just listening to the sounds in the water, and whenever there is something coming in that area, for example, what you call underwater vehicle from a different country, or a submarine, or something is moving in that, it will actually capture this image and suddenly come up, transmit a signal, and again go back to the water. So, nobody can detect the presence of such a spy there in the water, and this actually can be done with this module. So, you just change the buoyancy, it will simply come up, and you change the buoyancy, again it will go back. So, you do not need to have a continuous power to do this, only whenever you need to do some actuation you can give the power. So, that is basically the cascaded underwater modules. And again, this paper is available in the journal of IMechE Journal of Engineering for Maritime Environment. I think it is not yet in the hard copy, but the online version is available. You can go through it to get to understand what this can do. But now we are actually trying to do what you call an extension of this, seeing that how can we use this to design an underwater manipulator itself. Most of the underwater manipulators now use electric motors or hydraulic motors, and there is a lot of issue of sealing these motors and then maintenance of these motors. So, we are trying to see whether this module can actually be modified slightly, and you just have that module as at the joints, and then what you need to do is to just give a trigger to change the size, then it can actually get an actuation force, and then we can move the manipulator in desired direction. So, that is one work we are doing. So, and again one more work, one more thing what actually we did was we designed a glider using this module. Most of the underwater gliders use the principle of pumping water inside and taking water out to change the buoyancy, and that is the way how it works. And then this actually creates a lot of problem, because seawater has got a lot of highly corrosive, it actually spoil the system very fast. And therefore, we came up with a completely sealed one. There is no interaction with the environment, only a bellow will change its size inside, and it will keep changing the buoyancy. You will be able to get a change in buoyancy, and you can actually design a glider using that. So, these are the two current works in the area of underwater robotics, and we actually got filed 3 patents on this one itself, because we found that it has got high potential in future applications. So, that has been filed now. This is the work in underwater robotics, and Another recent work what we have been doing was is designing a telesurgical training robot. Most of you going a little bit more detail into this topic later, how design takes place or what kind of features are there should be there, it should be there in the surgical robots. And basically surgical robotic surgery is becoming more and more prominent nowadays. One reason is because of its technological advantages, other one is because of the publicity and other things gets. So, a lot of hospitals are moving towards robotic surgery. One of the main issue with robotic surgery at present in India is that we do not have many robots, and the existing robot, there is only one manufacturer of a surgical robot in the world, that is the Intuitive Surgicals, which actually sells a surgical robot called Da Vinci. This Da Vinci robot is costing around 12 to 15 crore for a single robot, and its running cost is also very high because the tool has to be removed, tool has to be replaced after every 3 or 4 surgery. So, each tool will cost around 1.5 to 2 lakhs. So, the running cost is very high. The main challenge is to the doctors is that how do they get trained into this system, because you cannot have a 15 crore robot and use it for training, and you cannot use the robot without training also. So, if you want to do surgery, you need to get trained on this robot. So, at present what those who are having money, they will spend their own money, get trained in some places where actually the robot is available, use the time. So, every hour is costly for this robot. So, you have to pay and then get the training. So, that is where when we thought that why do not we have something where actually the surgeons can use it for training, and then if possible we can actually convert that into a real surgical robot. That is why we started working on these robots. We got a DST funding, and then we developed a trainer robot which is proven in the laboratory. The next task is basically how do we actually take it forward and then make a robot. So, you can actually make it for 1/10 of the cost of the real robot. So, we can actually make it for 50 to 60 lakhs one surgical robot, where the trainer, where the actual robot will be costing around 12 crore. Okay, so that I will talk about the surgical robot little bit more as we move forward. And as part of this, we did a few other additional research work. One of my students was working on the tremor compensation in surgical robotics, because once the surgeon used the robot for long hours, 2-3 hours, then the hand data, and then to classify them and then predict what kind of what stage the tremor starts, and then how do you classify them as different levels of tremor, and then what kind of compensation can be done to reduce the effect of this tremor. There are few papers available in literature. So, if you search for tremor compensation, you will see that how this tremor is measured, how they are classified. And another issue is with surgical robotics is the stability issue in bilateral teleoperation. Because surgical robots are teleoperated robots, and you need to have a two-way communication. Two-way in the sense you send the signals and you get a feedback also. So, when you try to get this two-way communication, it is known as bilateral teleoperation, and when you have this bilateral teleoperation, the stability of the system and the transparency, where how much we can actually really feel the force sensing or the visual sensing, how much you can send this. Actually, there is a what you call some kind of balancing of these two. So, that is basically known as telepresence and transparency and stability. So, we need to look at these stability issues and then see how best we can actually get the feedback, and at the same time the system will be stable in the teleoperation. So, that is basically the stability issues in bilateral teleoperation. We are actually started working on this, still a long way to go. That was about the surgical robotics. And aerial robotics is very common nowadays, because everyone talks about quad rotors. So, we did not really want to get into the same kind of work. So, we were looking at as a design department, we were looking at how best we can design a better quad rotor. Okay. The existing quad rotors are all standard, and there are limitations in operation, because you want more payloads, you need to increase the size, you want this to run for a long time, you need to have a larger battery. You have a larger battery, the weight increases, again you need to have a larger propeller So, like that it keeps on going on. So, we wanted to look at how best we can improve the design of the quadrotor itself, and that is where we came up with a new design called the WOOPS. I will talk about this later. WOOPS stands for vertically offset overlapped propulsion system. It is a new concept. So, we actually try to reduce the overall size of the quadrotor by overlapping the propellers, as you can see here, by overlapping the propellers, and then trying to understand what are the effects of this overlap and how can we overcome them, and then get a better design for quadrotors. I will talk about it later. And in the mobile robot, we have been working on task allocation in mobile multi-robot systems and redundancies resolution in mobile manipulators. And this is work we did a few years ago. I mean, if you have multiple robots and you have a big mission, how can we actually divide the mission into sub components or smaller elements, and then you have multiple robots with various capabilities, not the same kind of robot. You have one robot with a particular sensor, another robot with a particular sensor or particular capability. So, how do we actually allocate the task based on the main task? How do you divide them and then allocate the task to different robots? Basically the task allocation problem in multi-robot, heterogeneous multi-robot systems. And then another work at present we are working on is the mobile manipulators, the redundancies resolution in manipulation, because mobile robots are inherently redundant, because the base has got degrees of freedom and the manipulator also has got degrees of freedom, and this redundancy in the degrees of freedom can be used for multiple application. One is for path planning, the other one is for getting obstacle avoidance. So, we are trying to look at these things and then see how the redundancy resolution will actually improve the performance of mobile manipulators. So, these are the major areas of my research work. So, you can see they are all into different fields: underwater, aerial, medical, mobile robots. So, I put them all together under field and service robots. I will tell you what actually that means. So, my work is mainly on field and service robots, dynamics and control. So, that is the I can say broadly we can say the dynamics and control of field and service robots with some design aspects going into it. So, apart from this robotic research, I have been working, because I am from the design department, engineering design department. So, we have been working on many design projects also, that actually led to a few products which are patented, and some of them are commercially also available. So, this was one of the products which I worked during my biodesign fellowship at Stanford. Okay, of course, it was not, it was actually we came back to India and then developed this particular product, and this product is now commercially available. It is a very simple, very low cost, but with lot of potential application in emergency care. This actually is only, I mean, it is a very practical application which all of you can relate to. If anyone meets in a road accident, there is a fracture or a major fracture your arm or your leg, you need something to protect you till you go to hospital or till the doctor attends to the limb. At present, you look around your there is nothing available in the market which can actually do this job, and people do all kinds of stuff. They will put some log and then tie it without any scientific protection, or without any support. They go to the hospital, and after 2 or 3 hours only the patient will get any treatment by the ortho. So, this product helps to simply tie the limb, protect it for 3-4 hours, nothing will happen to the fractured arm. So, it will be just remain there, it will not create any further damage to the fractured limb. So, this actually costs only 100 rupees. The existing products which are in the market cost you around 50 to 60,000, which are not disposable. So, this is a disposable product, 200 rupees, anybody can buy. It can be made available in medical shops. It is available in most of the emergency ambulances, and defense is using these products nowadays to protect their jawans from this kind of accidents or injuries. It is commercially available. There is a company called HLL Life Care in Trivandrum is manufacturing and selling it in the market now. and this was another product, a combinational scissor grasper for laparoscopic surgery. This was developed by one of my students during his master's thesis, and when he presented this to the company Intuitive Surgical. So, this is the company which makes the only surgical robot in the world in the US. So, they were interested and they bought the license and they are going to use it for their in some of their products now. Wound cleaning robots, of course, this has not been patented or licensed. We actually came up with the idea of designing a robot for cleaning wounds in the hospitals, automated cleaning of wounds. A non-destructive method to identify used syringes, this patent has been patented, and it is a very simple concept. It does not prevent the reuse of syringes. The main challenge in syringe reuse is that the syringes will come back to the market without they getting, though it has one time use, it will come back to the market. So, how do we actually know whether it is used or not? That is all it will do. So, if you want to use it, you can use it. If you do not want to use it, you know it is used. So, that is a non-destructive methods. And some other products for descaling the inner wall of a chemical tank. This is a patent already granted. And fetal growth monitor for rolled application, again a part of our biodesign program. We came up with a simple device which can be used for fetal growth monitor, and a proportion solenoid valve for space application was also developed as part of our design activities. So, that briefly tells you or gives you an idea of what are the kind of work we do, robotics plus some kind of a design job also, because I am from the design department. So, that is all about my background. Let us go to the topic of discussion. I think I took a lot of time. Let me go to the content. So, I will be briefly talking about two projects. One is on the surgical part robot, and the other one is on the WOOPS, that is the conventional the novel quadrotor what we have developed. Okay, let me briefly tell you what is the field and service robotics, and then what is the significance of this field service robots. As you know, the robotics came around somewhere in the 1960s in the market, and people started using robotic technology in industry. That is where the industrial robots came into existence, and you can see that from 1960 onwards, industrial robot was actually steadily progressing. And at the same time, many people actually came up with a lot of applications or lot of ideas how the robotic technology is going to change the world. But nothing much happened till 1990s. The only focus was on industrial robots, and after 90s only, when the industrial robots was coming to a saturation level where you can make robots, you can use the robot, but beyond that, what can you do? What is the development that can have in the robotics? And that is one of the reasons why robotics did not really progress the 30 to 40 years from 1960. The only progress was in industrial robots. And after that, people realized that you need to have more applications for robotic technology, because you are developing a lot of sensing, actuation, kinematics, dynamics, control and all. What are you going to do with all these? Then started thinking of how can you use this technology for various applications, and that is where these robotics, these areas actually started developing. So, from 2000 onwards, there is a lot of focus on all these robots, and these robots together we put them under the field and service robotics, where anything other than industrial robots can be generally classified under the field and service robots, and that is one of the main areas which actually propels the growth of robotics in the world. Any robotic technology comes into the market, unless you have an application, it is going to be of no use. You can just publish papers and then keep it, that is all. But when it grows is basically when you have a new application. Okay, if you can develop a new application using the existing technology, then you are actually pushing the growth to a different level. That is where you get robots for all kinds of areas. So, this is where actually the current focus of robotics is lying, and then that is going to propel the robotic technology in the future. Okay, so let us go to the teleoperated surgical robots. How many of you have seen a surgical robot? Have you seen? at least in the photos? Yeah, okay. So, many people would have seen at least in the photos. Okay. So, when surgical robot was introduced, there was a very big misconception about the surgical robots. So, what is this robot going to be? So, is it that a humanoid kind of thing will come and do the surgery, or doctor will be wondering what is happening and leaving everything to the robot to do the surgery? But telesurgery is basically just an additional help for the doctor. Okay. So, actually from if you look at the history of surgeries, you can see the open surgery was the norm till 1990s and all, that if you have seen a person who has undergone a open heart surgery, that is for if you want to change the valve or do some corrective surgery, what they do normally, they cut the chest open and then move the chest and then access the heart, do the surgery and close it. So, if you have seen a person with that kind of surgery, there will be a long cut scar on the chest, which actually shows that he has undergone an open heart surgery. So, that was the open surgery period, and then a revolution came in this, basically known as laparoscopic surgery or keyhole surgery. So, what actually keyhole surgery is that you, instead of cutting open the whole area, you make 3 or 4 holes depending on the type surgery, and put one camera through one hole, and then put 2 tools through the other tools through the other 2 holes. So, these 2 holes tool will be held by the surgeon, and then he will have a screen in which he can see what is there at the inner part without opening. He can, through the camera he will see, and he will do the surgery using this information. So, the patient will be lying on the bed, and the surgeon will be standing on the side, and there will be a camera and there will be a video projection, and he will be looking at that, and he will just move the tool. He wants to do a surgery, he wants to cut it or he wants to pull it, he will be looking at that, and then he will be moving the tool. He needs, of course, needs lot of training, and that was the laparoscopic surgery in 1990. So, the person has to stand, the doctor has to stand near the patient in a very awkward position, because he has to hold it like this, he has to look there and then do the surgery. It was very tiring and very much difficult. Of course, people are still doing it. That surgery is one of the most common surgery nowadays. There are a lot of laparoscopic surgeons in the country, and they are very much experienced in that one. So, they can actually do it. But then somebody thought, why should the doctor stand here and do all the work? Why don't we ask the robot to do this? In any case, he is looking at this one and then trying to do the surgery. So, let us take the surgeon away from the patient, let him sit comfortably in one position, and he look at the camera and then do the surgery using a robot. So, that is where the robotic surgery came into existence. So, what actually happens is that, let me go to this. So, what actually happens in the traditional laparoscopic surgery, surgeon is holding the tool and directly connected to the tissue, and he is doing the surgery. In robotic surgery, the surgeon won't hold the tool, but a robot will hold the tool, and the robot will be controlled by a robot. Okay. So, basically you have a master robot and a slave robot. So, it is known as master slave manipulation. It is already there in industrial robot. Master slave manipulation is very much there, especially in nuclear power plants and all. This is very much used. I think tomorrow you will have a talk by BARC person. So, he will talk about master slave manipulation and all. So, here surgeon will be having a master robot with him, and he will move the master robot the way he want the tool to move or the surgery to be done, and the same motion will be mimicked by the slave robot, and then you will get the tool motion at the surgical site. So, this is what the robotic surgery means. So, you do not have a robot independently doing a surgery. Only thing the robot will do is to follow whatever the master is doing. So, nothing more than that, nothing less than that. Of course, you can have different finer motions and all, but the whole control is by the surgeon using a robot master. So, you have a master robot, slave robot, master is controlled by the surgeon, slave does the job. So, what happens here? The surgeon need not hold the tool, heavy tool he need not hold, he need not stand and in an awkward position, he can comfortably sit and do the task. So, that is for the, that is how the surgical robot works. So, what are the advantages? One is that surgeon is more comfortable now. The other one is the tool holding is done by the robot. So, the robot accuracy can be really controlled, it will be much better than the human. So, all the kind of human tremor and other things can be avoided, you will get a much better accuracy. And moreover, you can actually get something called a motion scaling also. That is, if I move 1 mm, I can actually decide how much the slave can move. The slave need not move 1 mm, I can say you move only 0.1 mm when I move 1 mm. So, you can actually program the robot in that way. So, what actually happens, you will get much better accuracy for the motion, because the human hand has got some limitation in what is the minimum that we can move, but the robot can actually be made to be much better position accuracy resolution. So, you will get a motion resolution also, so motion scaling also. So, in most of the surgical robots, the scaling of 7 is used. That means, if the surgeon moves 7 mm, the robot will move only 1 mm. So, that you can get very fine accurate movements at the tool tip. So, these are the advantages of using a surgical robot for surgery. And of course, there are other issues like the how do the surgeon know how much force he is applying, what is the how do know whether he is really touching or not. So, that is basically known as a haptic feedback. So, you can have a haptic system, or there can be something called a haptic feedback, where you can actually measure the forces and then give back to the surgeon, and the master's robot can be designed with a haptic feedback. So, that when he is facing when the tool is touching the tissue and there is a force, same force can actually be felt by the master robot. So, you can actually give a feedback from here, from the tissue to the robot master, so that the robot master will have that feeling that what it will experience a force. This actually we are creating that force using by measuring the force, then you create a force over here, so that you will get a feedback also. So, this way you will get the feedback. So, when you give that feedback, then it becomes a bilateral teleoperation, and then the stability and transparency issues will come into play. So, that is where actually we need to do some research to overcome those things. So, that is the basic idea of a telesurgical robots. So, this I already told you. So, you can have a heavy tool, remote action and all those things, task on moving object can be carried out. So, these are some of the advantages of surgical robots. So, this is one thing which we need to keep in mind when we do a surgery, laparoscopic surgery. So, the tool will be inserted to the body, and this is assume that this is our skin. So, it will be this is an abdominal surgery. So, tool will be inserted, and it is this point, and this point is known as a trocar point, through which there will be something will be inserted, and that through that only the tool will go inside. This is known as a trocar point. So, one important requirement of this one is that when you insert a tool and you want to move the tool like this, the tool should actually move with respect to this point only. The rotation center of the rotation should be here, because if you want to move this like this, it should not move from this point, it should move at this point only. Okay, otherwise it will tear the tissue. Okay, when we do that, human can actually put that center and then do that task. So, we intuitively do that, we will make sure that this point, the center of rotation is this point. But when you use a robot to do that, if you attach this tool to a robot and you have a robot joint here, when you move the joint, then the tool will actually move with respect to this point only. You cannot really make it to move this point. Okay. So, this is one of the main challenge or main issue in surgical robots. You need to have something called a remote center of motion. Okay. The motion should not be at the joint where the motor is placed. The joint motion should be with respect to this point, which should be away from the point of where the motor is there. So, that is known as a remote center of motion. So, this is one requirement for any surgical robot is the RCM mechanism. Okay, RCM is not anything complex, it is being used in many other applications, but we need to have that RCM mechanism in the surgical robots. I will talk about that when I show you the design what we have for the RCM. Okay, so, this is the general surgical robot system. You have the surgeon sitting here, you have the master manipulator, you have the monitor, and this master manipulator will be having the same kind of a kinematic structure. Okay, if it is 6 degrees of freedom, this also will be having 6 degrees of freedom, it has got a gripper, this also will be having a gripper. So, it will actually imitate whatever is needed here. So, this is the master manipulator, slave manipulator, camera and image over here. So, that is how the system works. So, the doctor will be seeing the tool, this is the master arm, this is a commercially available one. Here the master arm, the doctor will be holding it and then he will be seeing through this eyepiece over here or the monitor depending on what mechanism you have. So, you can actually see here this one and then he will actually manipulate the tool using this master arm. So, this is the commercially available surgical robot which I told you, the Da Vinci surgical system. So, doctor will be sitting here and he will be seeing the site. Actually, there will be a projector also here for the assistants to see. So, they set up the robot first, initially they will set up, that is what they are doing. So, once it is set up, then doctor will do the task and they do not do anything, they will just observe it what is happening. So, this is the slave robot here. The slave can have 2 arms or 3 arms depending on the type of robot, and there will be a controller which actually do the forward kinematics, inverse kinematics, dynamics control, everything will be held in inside this controller. It is a bit complex system, but it has been commercialized. So, it is highly successful now at this stage. So, theoretically you can see that it is doctor is sitting here. Theoretically doctor can be anywhere in the world, because as long as you have a good communication system, a good reliable communication system, doctor can sit anywhere in the world, and if you can get the video and the control signals, he will be able to do the surgery. Okay, but as per the current practice or current the rules of the American regulatory agency, that is FDA, doctor has to be in the same room of the surgery. So, he cannot be even in the next room. So, this master robot should be there in the same room. So, that is only consideration of safety. So, if something goes wrong, they should be able to take back the doctor should be able to immediately take action and then save the patient. So, that is only a purpose, otherwise theoretically he can be anywhere in the world. Just show you a video for you to appreciate the way how it works. Yeah, it is actually a demo video. Again, this is the trigger point and this is the tool. This is how the doctor will be seeing it. So, this is the master robot. It is a small robot, but the same kind of kinematic characteristics. Okay. So, that is just give you an idea of what a surgical robot is. So, now let us go to the design of our surgical robot. Actually based on the same kind of a principle where we have a telesurgical operation, where you have master robot and a slave robot. Since our purpose was to do the training, we did not really go into the details of the safety aspects and other regulatory thing. We wanted this to this can be used by doctors in medical colleges, and they can use the real tissues to do the surgery. Other than human being, they can actually do all other kind of surgery. So, it has got the same kind of a structure. You have master robots, 2 master arm, a screen, then you have a controller and 2 slave arms and 1 camera arm also. So, you need to have a camera arm and 2 slave arms. So, 2 tools can be connected and a camera can be connected, and that can be controlled by using the robot, this master over here. Then you have something called brake and other things. So, you have 2 slave arms of 7 degrees of freedom, 1 camera arm of 2 degree of freedom, and a 2D vision system, and 2 master arms with the same 7 degrees of freedom, vision system, haptic feedback capability, clutch, brake and safety features, basic safety features. So, these are the basic requirements for any surgical robot trainer to be developed. So, the 7 degrees of freedom, I will show you how the 7 degrees of freedom comes, and there is something called the wrist motion. So, like the human wrist, we need to have the same motion. So, we need to have some additional degrees of freedom inside the human body where the tool goes inside. Okay, so it is like this. You have the master control, patient side robotic arm, a camera, and dual arm surgical manipulator, camera arm, surgeon vision system, robotic master control, master console, haptic feedback, actuator, etc. This is the system at a glance. So, you can have multiple I mean all these elements should be there in the surgical system. And how it is implemented? So, you can have the input panel, then the master arm and the clutch left and clutch right. So, clutch left and right is basically if you have the master arm, and it is like our mouse. When you do use the mouse, some point you will see that it has reached a point. So, you will just remove that and keep it in the new position to again start moving it. So, similarly, when you are using two surgical master arm, sometimes it will come very closer. Okay, your tools may not be very close because it is a scaled motion. Then you want to move this back and then again start the motion. So, you can use a clutch, then move it and then do it. That is basically the two clutch, right, left and right, then monitor, etc. Then you have the main controller, then the slave arms left and right, then the graspers, and then camera and the patient bed. Okay, patient bed is not part of the real control, but these are the systems that you need to have for a architecture of this. So, this one I told you about the trocar tube and trocar point, a remote center of motion mechanism. So, you need to have this remote center of mechanism to get the motion. So, you can see here the 7 degrees of freedom, fulcrum at trocar point, remote center of motion. So, that is one requirement. You need to have the fulcrum at the trocar point where it is entering, and from there you need to have the motion. So, these are the 7 degrees of freedom. You have up down motion. So, the tool needs to be up down, it has to go up and down, then in out and side. So, it has to go like this and like this. So, two motions inside. So, it has to go like this and like this. Okay, that is the in out, and the 3 wrist movements. So, the wrist point here you need to have yaw, pitch and roll. So, you need to have this motion for the wrist, you have to have this motion and this motion. So, 3 motions here, and then the gripper, that is the gripping action, that also is added as a degrees of freedom in this case. So, like that you will be having 7 degrees of freedom. So, you can see here this rotation, the rotation of this one should be with respect to this point, that is very important. This 1 2 motion should be with respect to this point. Then you will have the wrist movement also. So, you need to have a tool which actually goes inside the body, which will be around 10 to 12 mm diameter, need to have these joints here as well as the motion capability here. That is one of the biggest challenge in designing this tool. This is the surgical tool which will go into the body, and these motions. So, the wrist motion you need to have the roll, the up and down motion, and this in out and side can actually be achieved from the outside actuators. So, that is the 7 degrees of freedom that you need to get the slave arm. The same kind of a degrees of freedom you need to provide in the master arm also. So, how do you get this remote center of motion? As I told you, the tool is be inserted here and the tool has to rotate with respect to this point, and that can be achieved in different ways. Okay, one of the method is to use a double parallelogram method, or you can actually, this is known as a passive RCM. You can have a active RCM by having 3 degrees of freedom robot, and then can control these 3 joints to get that remote center of motion also. So, when I say remote center of motion, basically what it means is that the rotation of this tool with respect to out of the plane or in the plane, this plane in the plane motion like this, or out of the plane motion will be with respect to a center point somewhere here. So, the center point will lie along this axis, and where the intersection of these two will be the center point. So, this will be the remote center of motion for this mechanism. So, that is how you achieve the mechanism. So, you can see here in this kind of a mechanism, whenever you try to actuate this joint forwards, then you will be getting the rotation with respect to this point, and then this way out of the plane also you will be getting this point as the center of motion. So, this is basically known as the RCM mechanism, 2 degree of freedom RCM mechanism. So, you will be getting this rotation with respect to this point. So, this is one of the main requirement for a surgical robot, where the trocar point is at the trocar point will become the center of motion. So, this is the design what we made for this, basically a parallelogram mechanism. By the way, in case you have any questions or you want to get more clarification, please feel free to stop me. I can just discuss and then move forward. Okay. Otherwise, I am thinking that okay, you are able to follow and then just going ahead. Okay. Yeah. So, this is the mechanism. You have a linear slide for the linear motion, then you have one motor here and another motor here, and behind there is a motor. So, this motor will provide the roll and the other one will provide the pitch motion. And you need to have some static stability, static balancing, because otherwise it will just fall. So, at any position it should be statically stable. So, you need to add some static balancing weights. You can do a static balancing or dynamic balancing, but in general we try to do as much as static balance as possible, and then the rest can be balanced through some dynamic balancing method. So, this is the design what we followed for the RCM mechanism, and it has got reduced inertia, because we actually moved all this tool. You can see this is the tip of the tool where actually it has to have 3 degrees of freedom, and all the motors which are used for this will be somewhere here. Okay. And therefore, it has got reduced inertia, and then rope drive will be used to drive the tool from this point to change. So, you can see there will be 4 motors here for the 4 degrees of freedom, and all will be connected through rope to this tip, so that you can get the desired motion at the tool tip. This is okay. This diameter of this is 12 mm. Okay, and the whole thing will be around 45 centimeter. From if you take from here to here, it will be around 45 centimeter.
So, how does the rope drive work?
I will come to that. Okay, I will show you the rope drive, how the rope drive is connected. So, this is basically on the RCM mechanism. So, this is the RCM mechanism we have, and we have this mechanism. So, this mechanism will ensure that the RCM will be along this line, and along this line it will be somewhere here. So, you have to position your robot in such a way that that is the point where actually the trocar is connected, or trocar point will be this point when you insert the tool into the human body. So, this is how the tool is designed. So, we had some they are coupled actually. When you have one rotation, the other rotation also will get affected. So, you need to have a decoupled motion, and then we need to have some kind of design over here where we have to look at the path of the rope, and then how the rope path changes with respect to the motion, and we have to decouple it. So, we actually decoupled the degrees of freedom. So, you can see here there is a roll motion for this, there is a pitch motion, and then again a freedom for this one here also. The 2 degree of freedom will be for the grasper also. So, you need to control all this, and at the same time when you actuate one, the other one should not really move, because now these are all connected through mechanical like this. There is a possibility that when one is moving, the other one also is moving. So, we need to have proper design in a way that can actually be decoupled. So, we had a decoupled design, and we actually reduced the rope wire because of our design of this particular joint. We had a special design for that to reduce the friction. So, you can see here this profile was carefully analyzed and then planned, so that you can get a decoupled motion. So, the drive motors, all the drive motors will be here, and they will be connected to this joint to get the desired motion as well as the roll motion also. So, the rope will be actually coming from here and will be passing through this and will be connected to this point. So, you can see it now. We use the PVC cables or the ropes. Actually we need to go for metallic one. Metallic one will, this one will be having, after some time it will start having some kind of elongation. So, to avoid that, it is always better to go for a rope transmission. Unfortunately, the ropes are not really available for small quantities. We have to order for 1000 meters, and it's costly. So, we initially, being the first prototype or the lab prototype, we decided to go with this kind of nylon wires for transmission. So, the transmission actually comes from here. You can see there will be this is the motor, and it is connected, and there will be rope will be wound over here, and then it will be connected. It will be passed through this, and then it will come into this, and then connected to here. So, then it will go back and again wound. So, it will be winding of the rope as the motor rotates. That is how it actually is connected. Is that answers your question? Yeah. Okay.
Is there feedback for the tension of the rope?
At present, no. Okay. No, it's actually basically what we need to do is to initially at the setting up you need to make that it is slightly under tension. Okay, so that it will be always, it will not never go to a slack mode, because slack mode will not be tolerated. So, you initially tighten it and provide some tension, and then after use then you need to check that again. So, after 2 or 3 uses again you need to check whether it is maintaining the same tension or not. It is really needed to have a proper tension, otherwise you do not get it. And that is one of the reasons why this current surgical robots, they do not allow this tool to be used for more than 4 surgeries. After every 4 surgery you have to throw this tool and use a new one, and each tool costs around 1 lakh. It is one of the costliest part of this robot, because nobody can ensure that it will have the same kind of performance after 4 or 5 surgeries. Yeah, but their rope mechanism is slightly more complex. Actually, here we are actually putting all the motors here. Okay, in Da Vinci the motors are actually sorry, I can, yeah, motors. Now we have all the motors on this one. Da Vinci has all the motors somewhere here only. So, they take the rope through different mechanisms and then connect the motors here. So, they have a very long rope transmission, which actually again the efficiency and all those things are issues, but that is the way how actually they designed. But then we found that will be more complex for us to handle. So, we actually put all the motors over here. So, one drawback is that you will be having more inertia at this point and you need to do more compensation. Then advantage is that your rope transmission is directly connected to the motor without much of thing. Here they will be using multiple transmission. If you will see that there will be all the motors, the cables will be going through all this arm and then reaching somewhere here, and then the motors will be all there only. So, the another advantage for them is that they can simply replace the tool. So, here if you have to replace the tool, then you need to do a lot of work to disconnect from the motor and then do it. So, but since we are not really going for changing this for very frequently, because it is basically for a trainer, so we decided to move all the motors to this design, this point over here. Okay, so this actually shows the rope transmission and how it is connected. This is the prototype what we have. Okay, so this is how it looks like once you assemble all the 4 motors. So, you can see the diameter is around 12 mm for this one. In fact, if you can reduce it, that will be much better, but we could not really bring it less than 12 millimeter, because the fabrication of this part was very difficult. We could not, we tried many places here in India to machine it, but then machining will never, did not give us the desired profile over here. Finally, we could get it done using rapid prototyping, again from a US company. So, we have to send this CAD model to them, and they will analyze and then see whether they can make it, and then they will send it. They will make it and then send it to us the product. So, we actually got it done from a US company, all these complex parts. All other things we could do, but this part we could not do. We did 2-3 times in India, it failed. So, finally, we got it done from a company which is metal rapid prototyping. Okay, so this is how it will look like when it is all the motors are all our Maxon motors. We use Maxon motors and their controllers for this. Brushless DC servo motors. Okay, I will show you a video later. Okay, so that is the slave robot. So, you have this 2 degrees of freedom RCM, and then you have this 4 degrees of freedom here and 1 degree the gripper. So, you have the 7 degrees of. So, these are basically known as passive joints. So, you need the passive joints to position it, whatever the way the initial positioning is done through the passive joints, and once it is positioned, then these joints will be used for controlling the movement. So, like that we have the 2 slave motors, a slave arm with the 2 tools, and then is a controller. All the motor controllers are inside this chamber. So, you have the 7 plus 7 here, and then master also. So, you have 7 motors for each slave arm, then 7 plus 7 plus 7 plus 7. So, it will have 4 into 7, 28 motors plus the camera arm. So, if you have 2 degrees of freedom, 30. So, you have minimum 30 motors to do this job. you can roughly say that each motor combination costs you 1 lakh. So, the motor itself will be around 30 lakhs to make this single unit.
Is the master robot scaled one?
No, master is full this one. So, scale in the sense you are asking the prototype? No, this is actually the full scale version. Okay. This is the full scale version, because we actually identified the required workspace for this. So, the basically it depends on how much it has to move up and down and what is the angle requirement. Accordingly, you have to make this. And this one, this design is basically where you want to place and how much freedom you want this to for positioning. So, this size depends on that. Okay. But otherwise, it is this, if assuming this is a table, then you can see this is the requirement for it. Just the first prototype. I think this video is there. I will show you a full video later. So, this is only the RCM part we are showing here. So, the RCM will be somewhere here this point. So, you can with respect to this point only it should move. So, it may not be 100% accurate because of our fabrication issues, but in general the RCM should be with respect to this point. So, only these 2 degrees of freedom we are showing here. Okay, next is the master arm design. So, master arm again the same number of degrees of freedom, 6 degrees of freedom plus the grasping action. You need to have static and dynamic balancing, because the doctor should not feel too much of weight on his hand, and haptic feedback, ergonomic design, decoupled positioning and orientation. Because you want to change the orientation of the tool or you want to change the position, you should be able to do it in a decoupled fashion. So, we did a design which is completely different from what the Da Vinci is having. So, we have this design where we have a gimbal over here, and then this is the gripper, and this orientation is independently controlled and positioning is controlled by using these joints here. So, you have one motor here, another motor here and another motor here. So, you have 3 degrees of freedom over here and the 3 degrees of freedom for the orientation and one for the grasper. So, like that you have 7 degrees of freedom. All the motors are placed over here, so that you will be able to get balancing, easy balancing. So, motors are all placed here and you have the counter mass also provided here. This is the CAD model, final model. So, you can see there are no motors over here, and this is so actually you do not really need to have a motor as such, because you are actually moving it passively, and there will be what you need is only encoders over here. So, you have the rotary encoders, you can actually calculate the joint motion and then do a forward kinematics to see how much the tip has moved over here. What is the position change, what is the orientation change can be calculated by using the position changes. So, you just measure the joint angles and do the forward kinematics, you will be able to get what is the position and orientation change for the tool based on what you are moving, and then take that and do the inverse kinematics and then give the same to the slave arm. So, that slave arm will move and then get the same tool tip motion. That is how it works. And why we provided motors here was to provide the one, you can actually have a dynamic balancing if needed, and 2 you can have a haptic feedback also. So, you can use these motors to load the joint depending on the force it is experiencing. So, if you have the force data coming from the surgical side, you can use that and then load the motors, so that you will feel the motion resistance. So, that is where you need to have the motors over here. So, provided 2 motors, so that you can have a haptic feedback, and then you can have the gravity compensation also, inertia and gravity compensation also using motors. So, 2 purpose can be served if you have a motor. For the time being, we are actually using it as passive initially for the trial parts. So, static balancing of system, additional dynamic compensation possible, provision for haptic feedback. Any questions? 7 degree of freedom and innovative grasper design. So, the grasper design was also an innovative one. I am not sure that it is here, because we wanted to have it completely different, so that you can really get the grasping motion, smooth grasping motion compared to what is available presently in the Da Vinci system. Okay, so you can see here, this is the grasper, just got a sliding motion, and the profile is defined in such a way that you will get a smooth motion, and then you can get the grasping action at the other end. And this is the prototype of the arm. Yeah, this is the gripper design. So, once you press this potentiometer, there is a linear potentiometer. So, this will be actually moved in this direction. So, that motion will be taken as a input, and that will be used for controlling the slave gripper. Camera arm, we did not do anything, we has made it as a just simple one. You can actually move around 1 degree of freedom, can go up and down also. So, 2 degrees of freedom camera. It is a 2D camera we decided, because 3D camera is very costly, it is not worth at this moment. So, we did not go for that. I briefly mentioned about what is haptic, basically to get that feedback so we can, based on the measurement of the contact forces, you can give a force feedback to the surgeon. And the controller is implemented like this for position control. So, you have a position PI control, speed and the torque control, then the PWM, and then motor control, and that data is taken back and then fed as feedback in an FPGA controller. So, single axis control for each robot, I mean each joint, you will be having a controller, then motor driver, motor, emergency brake. So, motor driver and a controller, and then that will be given to the encoder data will be given back to the slave side controller. So, like this, for each joint you need to have the position, velocity, current check, the status check, and then that will be sent to the controller, and controller will decide what should be the next action. So, each motor is connected to its own EPOS. We use the EPOS controller, which I gained from Maxon. Okay, so, as you can see, for each one you will be having this kind of control. So, it should be mapped to the slave arm. So, master arm, motors, we have used a MyRio controller for the master, and even SBRIO for slave arm and PC. So, all your coding for the forward, inverse and everything will be done, will be coded into these controllers. So, it will just collect the data, pass it, and then it will calculate what should be the motor joint motion to be done, will be calculated, and that command will be given to the motors. Okay, I do not want to go into the details of this, basically how you implemented the whole thing for the system. So, you can see because there are so many motors and controllers, so you need to have a proper system diagram to understand how it is working. Okay, so let me tell you finally what we achieved. So, this is the master arm, you can see it is the gripper, and the encoder is there at every joint. So, it will actually measure the joint motions and then calculate the forward do a forward kinematics, and then do the calculation of tool position and orientation change. So, how much the grasper to be opened also is decided. This is the tool, surgical tool. So, these are the different motions possible. You can see it is very small, though it appears to be very big in this case. Okay, it is a 12 mm diameter total, and these are the motions possible for the gripper. All these driven through the cables only. So, being the first prototype, it is not designed to have ergonomics and other issues or the appearance. This is the master, 2 master arms, and this is the video that you can get, and then you can see this person is controlling the master, and then he is actually able to move it. And there is a small delay which is obvious, because it has to be calculated and then communicated, the video to be communicated, based on that he will be able to see it. So, the delay actually accepted delay is 300 milliseconds as per the teleoperation. 300 milliseconds is acceptable, what we are getting is around 400 to 500 milliseconds, which need to be controlled by improving the communication and other things. So, that is actually shows how we actually designed and then built the surgical robotic trainer. Any questions? Okay. So, I will briefly talk about the WOOP system, that is the vertically offset overlap propulsion system. So, as I told you, the requirement for any quadrotor is basically you want to have good payload capacity, good endurance, but you do not want this to be very big. So, how do we actually make the micro aerial vehicle or micro robots with good endurance and load carrying capability. So, in general the quadrotor is basically known as a vertical takeoff and landing system, VTOL. So, it is that is the importance or the capability of the system, that unlike other aerial robots, it need not have a runway to take off, it can actually take vertically up, that is VTA, vertical takeoff and landing system. And it has got all the 6 degrees of freedom, it can actually go XYZ motion and then all the rotation motions. Only thing, it is 2 coupled degree of freedom. So, it cannot really move this way or this way, because that are all controlled, because so only 4 degrees of freedom are independent and 2 are dependent on the other 2 motions. So, endurance, payload, stability, maneuverability and footprint are the major concerns of any design of such a system. We want large endurance, good payload capacity, and the system should be stable and maneuverable, and as far as possible the footprint should be small, so that you can actually use it for many applications. So, how do we actually maintain this one, because they are not most of them are contradictory. So, if you try to reduce the size, then your payload will come down, endurance also will come down. Okay. So, they are not really possible to do it. So, we actually gone through the, I mean various options are there to do this, but none of them really lead to a designed or desired performance because of various considerations. So, we actually started looking at from a design point of view. We try to develop a quality function deployment. Those who are into product design will understand that this is one of the tools normally used in product design to understand the design dependencies, and then what are the contradictions it is existing and which are technically challenging, which one to be moved, and all those things can be studied using this kind of a quality function deployment. Basically, we write down all the functional requirements, we like all the metrics which are actually related to that particular one, and then we will try to understand which one is going against what. So, minus shows that there is a contradiction, plus shows that there is a positive effect. So, by looking all these things, you will get an idea what is the best thing that you can do in order to get a improved design. So, that is what we used to understand the design of this system. Okay, so this is just an explanation, and finally, we looked at we wanted to have this thing, maximize the payload capacity, maximize the endurance and minimize the footprint. So, after looking all these things, we tried to the propeller size and then the frame weight and this frame size has got a correlation. So, looking at these correlations and positive aspects of different parameters, we decided to go for something called a offset and overlapped propulsion system. So, that was one of the ways in which we can actually get our required parameters. So, what actually it does is that what you need to do is, instead of having all the propellers in the same plane, you have 2 in a different plane and then overlap these 2. So, that you can actually the overall size can be reduced without changing any other thing. So, we are actually reducing the size, but we are not reducing the overall size we are reducing, but we are not reducing the propeller size. So, this way you can still get the same kind of endurance and capability, but the size comes down. So, that was the idea of the WOOPs, vertically offset overlap propulsion system. So, this is the vertical offset and this is the overlap. So, you can see there is an overlap. So, how much overlap, how much offset, that is to be decided. That is actually more of a, this is more of a concept of how can we improve the performance. So, multi-rotor with the vertically offset overlapping propulsion was actually patented based on this, and there is a paper on in ICRA 2015. ICRA 2015 there is a paper on this. So, if you want to know more about, you can actually refer to that. That was the design, but as a concept it looked okay, but then we need to prove it, why it is good or how it is good and what makes it good. So, we did lot of analysis to see what will happen if I am overlapping two propellers, is it going to affect my propeller thrust itself. So, if it is going to affect and we are losing the thrust, then there is no point in overlapping, okay, because if that actually makes it worse, or the thrust we are losing lot of thrust, then there is no point in doing that. So, we wanted to analyze it and then use the blade momentum theory to understand the way in which the blade works. So, we looked at the thrust generated and the thrust coefficient, and then we actually converted this into two parts, where actually one is the loss due to thrust. So, we actually I do not know where I have the equation here. So, the CT is the thrust coefficient for a propeller, and then this CT we divided into two for the overlapped portion and the non overlapped portion, and then we tried to find out what will be the CT loss, and then once you know the CT loss because of overlap, you will be able to calculate what should be the loss in the propulsion thrust. Okay, so, we did this using then again did the dynamic model, and then try to understand how much the thrust will be lost and what will be the variation in thrust because of the omega L1. These are the speed L1, L2 is the lower 1 and 2, U2 and U2 are the upper 1 and 2, and T loss L1 and T loss L2 are the loss in thrust due to in L1 and L2. So, the lower thrust will be affected because of the upper one will not get affected because it is always getting the air from the top, but the bottom one will be affected. So, we are looking at how the T loss L1 and T loss L2 are going to affect in the dynamics of the system. And similarly, for the rotary, this is for the linear dynamics for the linear motion, and this for the angular motion, and this for the linear motion acceleration, angular motion acceleration. And after all those things, we try to understand what is going to happen when you have a overlap. So, this is the loss due to overlap. So, we try to understand this area. So, this area is the one which actually gets overlap, and that actually can have different configurations depending on the position of the propeller. I mean, you can have full overlap or a less overlap. So, various overlap are possible. So, we try to find out what is the T loss at the lower propeller L1 or L2, and we identify an equation to do that, and then did this analysis and calculated the thrust loss and generated a graph like this. What will be the loss in thrust because of various conditions L1 RPM and R2 RPM. Okay, so, thrust loss in the overlapped region of a lower propeller for various speeds of the upper and lower propellers can be computed. Maximum losses due to overlap occur at higher rotor speeds. So, we actually found out and then tried to plot this and for a particular one, and then we generalized it for this is for the condition offset 370, overlap 20%, what will be the variation this one. And then we plotted this, and we found that for any thruster, if you take the conventional or whoops quadrotor, conventional is one without overlap, whoops is with overlap and offset, we can see that the size of whoops can actually be increased with a or the propeller. If you take the same tip to tip size, suppose you want a 100 tip to tip size, the centimeter as the dimension, then conventional can have only a 15 inch, but this one can have around 20 or 18 inch propeller for the same tip to tip size. So, for the same tip to tip size, you can have a larger propeller without any loss in propeller, without considering the losses also. You can actually see that the propeller size can be increased without losing the endurance or losing the payload capability. That was one of the understanding from this one, and with the analysis of the overlap. Similarly, the offset, okay, this is basically to prove that. So, we did theory, and then we wanted to prove that it is correct. So, we developed a test bench where we have this propeller, upper and lower propeller, and then we try to understand the overlap and offset both can be controlled, and we did a lot of experiments and then showed that whatever theory that we got is correct. So, we used it. Okay. So, this was an experiment, and this actually shows that the thrust loss percentage loss is actually overlap. When the overlap is 10 to 20%, the loss is almost nil. You can see the percentage thrust loss is almost 0 till 20% overlap, 20 or 25%, and then as it increases, the percentage the loss increases and it actually saturates around 80 to 100% and 90 it actually saturates. So, as long as we are using in this region 10 to 20 or 20 to 25% overlap, you can see that the thrust loss is almost 0, and therefore, it is not going to affect your performance in terms of the thrust generated. So, that was one understanding. So, as long as you go to this level, there is nothing to worry. And of course, the drag loss is the other one which actually helps it to move forward. So, that is also almost very less even for the large percentage of overlap. So, we found that overlap has nothing much to do, I mean it is as long as you can control it, you will be able to maintain a performance. Okay, then again, as you know, the payload capacity also need to be checked. So, we actually tried to find out what will be the optimal battery capacity and the flight time in order to get the understand how the whoops will perform better than the other conventional one. So, once you know this, then this your consideration is basically how do you actually decide what should be the best way to overlap and what should be the maximum overlap and minimum overlap you would like to have. So, the percentage overlap maximum we found that is possible only 41%, because of the consideration it will just go one over the other, or this you will not be able to make it less than this because of the 4 propellers. So, maximum overlap that you can get is only 41%. So, if you make it to 20%, you will be able to, there will not be much of a loss also. And the other one was vertical offset, how much you can offset from the top propeller to the bottom propeller. So, one is that there will be a tip deflection as it rotates. So, it has to be overcome. The other one is how the airflow gets affected. So, if you plot the airflow, you can see that actually like this, the airflow will be like this. So, as long as you are beyond this, it is not going to matter much. If you are within this, then there will be some effect, but if you are beyond this, there will not be much effect. So, if you can actually make the offset somewhere close to this, then you are actually safe and it is not going to make much of a difference in the propeller efficiency. So, these two understanding we. So, once we did it theoretically, we started looking at the making it and then testing it, and to prove that. So, we actually set up did a lot of analysis, theoretical analysis with different comparison for the designed quadrotor, and we can see that for a whoops quadrotor we actually use got 21 minutes compared to this is at 19.6 with the 7.7% gain, and payload gain is very high, you can see around 62% payload gain you can get, and like that you found that you will be lot of gains in using whoops quadrotor compared to a conventional one. I do not want to go into the controller design. So, we actually used the PI-PID control as an initial setup, and then found that there are some issues with PI-PID, and so went for backstepping controller later, and then implemented the backstepping controller also, because the PI-PID was showing some kind of coupling effect, because one axis it was not able to really control the movement, and therefore, we went for changed to a backstepping controller. So, these are PI-PID controllers. So, actually in the presence of current, suppose the quadrotor is hovering at position and there is a current acting on it, how this actually will change the position, how the controller will be able to maintain it. So, we studied and we found that it is improving. Okay, let me skip this. So, one issue was with this, so that it was not able to control the pitch, it was able to control the roll, but the pitch, there was an undue effect on the pitch, and therefore, we wanted to go for a different controller. So, the undesirable pitch due to the input of both the axes, the PI correction after the error has happened. So, we went for a backstepping controller and then introduced the backstepping controller, and finally, we could actually get a much better performance compared to the PI-PID controller. And this is the whoops quadrotor what we made. So, it has got an overlap of 20% and an offset of 3 centimeter. So, the overlap is 20% and an offset of 3 centimeter, and we did since it is difficult to fly it and then do all the testing, we actually made a test platform where actually we have a universal joint over here. So, it can actually do all roll pitch motions, and then we commented a backstepping controller use, and then we controlled it and then tried to get all the feedback and then check whether it is we are getting the desired performance or not. So, this test bench was built, and then the quadrotor was attached to it and it was run to have different positions. Let me skip this. So, finally, we actually tested this for various load conditions also, because when we submitted for a journal, they wanted us to show them a video that it can really work. They were not really believing that it would work. So, they said, okay, you show us video. So, we actually run the video for various testing conditions. So, it has actually used for this actually shows a load carrying capacity. So, for various loads how much endurance. So, we run it for various loading condition. So, this is not the perfect way of loading, because this actually there is an effect of this rope and this movement, but it was necessary because if you have a load attached to it, it cannot really land on the floor properly, and when you have this kind of system, this weight can actually land at one position, then slowly we can land the quadrotor. So, we actually did this test for various loading conditions and then run it for to the flight time, and theoretically calculated what should be the run time and practically what we are achieving, and then we provided all the data to the journal. Then they were happy, so they accepted the paper finally, saying that yes, it works very well. Okay. So, this paper will be appearing in the Journal of Intelligent and Robotic System shortly. We just accepted recently. Okay, just one more. Okay, I will stop in another 2 minutes. So, we actually use it for aerial mapping mission also, because you have an increased payload capacity, increased endurance. So, we wanted to use it for creating 3D maps of area. So, we wanted to prove that you can use this one for creating 3D maps. So, we actually used our 3D stadium in IIT Madras and used this for with a proper waypoint planning and zigzag planning, and using a particular camera. Using the camera resolution, we decided what should be the gap between these two, and then use it, so that you can create get 2D images and then convert into 3D and create a 3D map of the stadium. Okay, let me skip these things, how the course correction result. I will just go to the so this is the trajectory what simulated. So, it will start from here and go like this, come here, and then so whenever it is overlapping overshoot, it like controller will bring it back and then again get into the path and then do this. Oops, okay, not able to show you the this video also. So, basically this 2D images were collected and then we created a 3D map out of it, so that you can actually get a 3D view of the whole arena or whole area, and that can be used for many other planning applications. So, this was another one which we use for this the quarries were actually collect the stones and then they damage the whole area by collecting stones. So, we can use it and then identify to what extent their depth has gone, what is the way in which they have done the quarrying, and then how much damage it has created. So, just by taking 2D images using camera, we can stitch the images and create a 3D map and then find out what is the depth at different levels, and then can have multiple applications of using that one. Okay, so with that let me conclude. This is actually for a theoretical framework was proposed and experimentally validated, and backstepping controller was developed for the whoops, and finally we implemented it for various applications also. Okay, thank you very much. I hope you got some idea about these two topics. In case you have any questions, I will be happy to answer. Thank you very much.